We are in section 4.4, and the section is Oxidation Reduction Reactions. These are sometimes called redox reactions. And this is a reaction where electrons are transferred from one substance to another. So any redox reaction occurs when electrons are transferred between two substances. And we have a special little mnemonic for this. You might be wondering what the funky little red and green is over on the right side of the screen, and you're about to find out. Leo, the lion. You're starting to see a picture of a lion. What do lions say? They say grrr. All right, this is just a little mnemonic for memorizing that losing electrons is oxidation. Losing electrons is oxidation. Gaining electrons is reduction. So Leo the lion says grrr. And so we have over on the right side a lion named Leo. And what does Leo say, everybody? That's right. Leo says grrr. So in order to learn about redox reactions, you have to learn something called oxidation states. Oxidation states are the same thing as the term oxidation number. And an oxidation number, okay, I paused for a minute there. I don't know if you noticed, I'm focusing on fixing my handwriting a little bit, and I just fixed oxidation number there. I noticed it was very messy. Okay, oxidation states are a way of identifying whether electrons are gained or lost from an atom. It's not exactly how many electrons, well, it's not at all how many electrons an atom does or doesn't have, or an ion does or doesn't have. It's just a way of keeping track of where electrons came from and where they went. So we have to start out with some rules for assigning oxidation numbers. Here's a chart. We have different substances and their oxidation states. So for pure elements, the total oxidation state is always 0, or the oxidation number is always 0. For monatomic ions, single atom ions, the oxidation state is the charge of the ion. For polyatomic ions, now notice polyatomic, what does poly mean? That's right, it means many. So many atom ions, polyatomic ions, the oxidation state rule is that all the oxidation states of all the atoms in the polyatomic ion must add up to the charge of the polyatomic ion. Another rule for all compounds. Now remember, a compound is a substance with no charge with at least 2 different elements in it. We learned that a long time ago. For a compound, all the oxidation states of all the atoms must add up to 0 in the compound. If fluorine is in a compound, its oxidation state is -1. If hydrogen is in a compound, its oxidation state is +1. Remember, pure elements, the oxidation state is 0. So these last 3 rules are only when you're in a compound. For oxygen, the oxidation state is -2. Now, rules above take precedence over rules below them. That's very important. I just made a little note that the rules above take precedence over rules below. So if 2 rules contradict one another, you use the rule higher up in this chart. And you will see times where sometimes the rules do, in fact, contradict each other. All right, so let's do some problems. What is the oxidation state for each element in each substance? So what we do is we check our rules. First problem is copper. We go up to our rules. Copper is a pure element. Pure elements all have an oxidation state of 0. Therefore, copper has an oxidation state of 0 for pure copper. Let's go on to the next problem. Copper 2+. Let's find a rule. Hopefully you're recognizing that copper 2 plus is an ion because we have the plus 2 in there. And is it a monatomic or a polyatomic ion? Does it have one atom or more than one? It has only one atom, so that would be a monatomic ion. So the oxidation state is the charge of the ion. Cu in copper 2 plus has an oxidation state of plus 2. And the last one we will do on this particular page is chlorine. Now, chlorine is a pure element because there's only one element in here. We go back up to our rules, and again we have a pure element, so the oxidation state is 0 for each chlorine. I do not write Cl2, I just write chlorine over here because each chlorine has an oxidation state of 0 since it's a pure element. All right, we're going to do a couple more problems here. Now, if you feel like you know how to do these, you shouldn't know how to do them yet. There's still some more complicated problems. But, you know, it's up to you if you want to try these on your own or if you want to just follow along with the video, completely up to you. Okay, so ClO4, 1 minus, is a polyatomic ion. So let's look at our rules. Note we have a polyatomic ion. We've got two different elements in there, and the charge is -1. So let's check our rules over here. And our rules, polyatomic ions, all the oxidation states of all the atoms must add up to the charge of the polyatomic ion. So when we add up all of the atoms, the total of all the oxidation states must add up to -1. And what else? Oh, we have a rule about oxygen, which was in the polyatomic ion. Oxygen is -2, and none of the other rules are going to contradict that, so we are going to use that rule. Now, we're going to put single atoms up on top, very similar to how we did naming ionic compounds. We would put single atoms on top and the totals on the bottom. So each oxygen we just learned is -2. I have 4 oxygens. So the total for the oxygen is what? -2 times 4? Hopefully you got -8. Okay, now the total charge on the polyatomic ion must add up to the total charge of the ion. The total charge of all the oxidation numbers must add up to the charge, which is -1. So I have -8. I have to figure out what is the chlorine going to be to make this sentence true. What minus 8 is -1? Yes, 7. I have only 1 chlorine. So the oxidation state for chlorine is 7. So chlorine is +7. And each oxygen, I don't write the total, each oxygen is -2. So notice I don't write -8, I just write what the actual number is for each oxygen. Okay, number 5. We've got chromium, phosphorus, oxygen. This is a compound because there's no charge shown up here. So the total, when you have a compound, if you look at your rules, the total has to add up to 0. Now I know each oxygen is going to be -2. I just learned that in my rules, and I used that in the last problem. But I don't know phosphorus or chromium. What happens here is I have to pull the phosphate here outside, and I'm going to do the P separately from the whole chemical. I look up phosphate, and I see the total charge for phosphate. It's PO4 3-. I know the oxygen already is -2. -2 times 4 is -8. The total here has to add up to the charge of the polyatomic ion, -3. So I say, what minus 8 equals -3? Hopefully you got it. 5. That tells me that the phosphorus has an oxidation state of 5. And I go back to the original problem, and I'm going to erase this side information over here. Now back to the original problem. Let's get our totals right now. It's a little confusing. The oxygens, how many oxygens do you think I have? Hopefully you're not saying only 4, because I have 2 phosphates. So the total number of oxygens is 8. So my total oxidation state, I have -2 times 8. I'm sure you know that that is -16. Okay, phosphorus, 5, and I have 2 phosphoruses, so the total there is +10. Now what do I add to 10 minus 16 to make this whole thing add to 0? Hopefully you realize it's 6. 6 plus 10 minus 16 is 0. Now, the total chromium is 6. How many chromiums do I have? Do you see it? There's 3. Good. All right. If I have 3 chromiums and they must completely, totally, all together add up to 6, what is each chromium by itself? Hopefully you got it. +3. No, +2. Sorry about that. So each chromium should be +2. All right, another chemical. This is called hydrogen peroxide. You don't need to know that name. It is a compound, so the total must add up to 0, whatever that total is. Now we have hydrogen and oxygen. Neither of these are pure. It's in a compound, so neither of the elements on their own is 0. But let's look up our rules. This one's going to get a little complicated. We have a rule that says H is +1 and a rule that says O is -2. If I use those 2 rules, then the rule that compounds must add up to 0 cannot hold true. And remember, rules above take precedence over rules below. And because of that, this is the rule that we cannot use. So we're going to use compounds add up to 0, and we're going to use H is +1. So H is +1. The total on the H's, I have 2. What's the total? Good, +2. The total on the oxygens, if we want this whole thing to add to 0, must be, yes, -2. I have 2 oxygens, so each oxygen must be what? Hopefully you got it. -1. All right, let's put our answer over on the right side. All right, last problem on this page, peroxide. We have a polyatomic ion, and we're told that polyatomic ions have to add up to the total charge of the ion. The total charge here is -2. So I cannot use the rule that oxygen is -2, because if it were -2 and I have 2 oxygens, the total would be -4. But it's not. The total is -2. So I'm just going to write, I only have 1 element. Total is -2. I have 2 atoms, and they have to equal -2. So each atom is, hopefully you got it, -1. So here, the oxygen is -1 in the polyatomic ion called peroxide. All right, at this point, if you want to go ahead and pause, solve these on your own, and check your solutions. The actual solutions are up on Edline. I am going to go through and solve these for you, but you don't need to watch this if you don't want. All right, here we go. Number 8, we have a compound. Total must add to 0. Oxygen is always -2. Hopefully you can recognize this is an ionic compound, and in ionic compounds, the ions are actually just, the oxidation state is the charge of the ion. So I know sodium is +1 because sodium is in the +1 column. It's an alkali metal. But let's just check if indeed we do add up to 0 here. O is -2. Sodium +1 times 2 atoms, +2. And I haven't contradicted any rules. It's always good to make sure your rules are okay and you haven't contradicted any. Okay, next one. This is a compound. The total must add up to 0. Hopefully you recognize you've got a metal and a nonmetal, which means you have an ionic compound. So I can just look up the charges of the ions. Chlorine is in the -1 column. I put a -1 up there. I don't know copper automatically, so I'm going to find the total on the chlorines. 2 atoms. Each is -1. The total is -2. Therefore, in order to make this whole thing add up to 0, copper must be +2. There's only 1 copper, so each copper is 2. Last but not least, we've got, again, a compound. The total must add to 0. Oxygen we know is -2. We don't know what the manganese is, and I don't know what carbon is. So what I'm going to have to do is recognize I've got a polyatomic ion in here, and I'm going to pull out my polyatomic ion. Whenever you see a polyatomic ion, pull it out of the problem, and you can always solve for the second element in the polyatomic ion using the charge of the polyatomic ion. So this total must add up to the charge of the ion, -2. Each oxygen is -2. Total on the oxygens is -6. In order for this equation to be true, the carbon must be 4, because 4 minus 6 is -2. So I put a 4 up on the carbon, 4 up here. And now let's get the manganese. We can just use the total adding to 0 at this point. So oxygen, -2 times 3 is -6. 1 carbon, 4. So my manganese must be, that's right, +2. Okay, really important. I keep saying this. When we write the oxidation states, it's for each atom, not the total. So for oxygen here in number 10, the oxygens are each -2. I do not put the total of -6 for the oxygens. All right, there's one last thing that we're going to learn here. Okay, we have some new vocabulary. I just took a peek at that and saw that I had been writing too quickly and misspelled vocabulary. So there we go. Vocabulary's all fixed. So we have some new vocabulary. The first vocab word we're going to learn is an oxidizing agent, which is the reactant in a reaction that gets reduced. Remember, gaining electrons is reduction. Leo says grr. There's also something called a reducing agent, and the reducing agent is the reactant that gets oxidized. Losing electrons is oxidation, so Leo. Okay, so we're going to do some problems. For the following problems that you can't see yet, but you'll see soon enough, you're going to identify the element oxidized or reduced and the oxidizing and reducing agents. So let's take a look at number 1. This equation is already balanced. What you need to do here is identify all the oxidation numbers on every single element in all reactants and products. So CH4, we know the total has to add to 0. We look at our rules, we see H is always +1 in a compound. I have 4 H's, so this is +4. Total adds to 0, so the carbon must be 4. I'm going to keep going. Oxygen, pure element, 0. By the way, when you are doing oxidation numbers, ignore the coefficients. Ignore, this is really important, the coefficients for oxidation numbers. You don't ignore subscripts, but you do ignore the coefficients. Okay. CO2. O is -2. The total, this is a compound, not an ion. Total adds to 0. Oxygen, -4 total. Carbon is 4, +4. I just realized there's a mistake back here. This carbon over here is -4, not +4. You probably were wondering what I did wrong over there. I am so sorry. 4 + 4 is 8. So, oops. -4 + 4 is 0. Okay, so on CO2, did everyone catch that? Good. Carbon over here, -4, not +4. Okay. Carbon on this side is +4. Water, we're going to ignore the coefficient. We're just going to ignore that. It's there, but it doesn't affect the oxidation numbers. O is -2, and there's only one of them. This has to add to 0, so the hydrogen has to add to 2. And we also have the rule that hydrogen is always +1. +1 times 2 is 2, so this works, along with the rules about hydrogen and oxygen. Okay, we've got all of our oxidation numbers. And now we need to identify the element oxidized or reduced. So let's find out what changed oxidation numbers. Anything that changed in oxidation number gained or lost electrons. I see the oxygen goes from 0 to -2. Now let's think, if you go from 0 to -2, are you gaining or losing electrons? Electrons are negative. So if you become more negative, you are gaining electrons. Gaining electrons is reduction. This is reduction right here. Also, if you notice, the charge 0 down to -2, the number reduced, reduction. That's where that reduction word is coming from. Okay, let's find out what element got oxidized. Okay, I've got this funny feeling that I was on pause when I was supposed to be recording. I'm not sure, but if I was, I apologize, and this next problem, you'll get to hear everything while you won't just see the final result. You'll see everything being done as it was being done. So if you're confused, don't panic. We're going to go through another example. Okay, now, we want to identify the element oxidized, that was carbon. The element reduced was oxygen. And we look at our definitions. The oxidizing agent is the thing that gets reduced, the whole reactant. So the whole reactant that got reduced was oxygen, O2, and this is the oxidizing agent. It's a little confusing. If you get reduced, you're the oxidizing agent. And the reducing agent is the reactant that gets oxidized. It's the whole reactant, not just the element. So CH4 is the reducing agent. And I will go through one more example problem on this. If you figured it out, you can just move forward. If not, just listen. Okay, so when you're doing these problems, you have to assign oxidation numbers to every single thing in the entire reaction, every element in the reaction. So over here, hydrogen, H2, pure element, 0. Oxygen, O2, pure element, 0. H2O, it's a compound. The total must add to 0. Hydrogens, when they're in a compound, are +1. Oxygens are -2. But let's just check to make sure that this does add to 0, because we don't want to have our rules contradicting one another. So 2 minus 2 is 0. All righty. We're good. We've got our oxidation numbers. Oh, one very important thing. When you're assigning oxidation numbers, you ignore the coefficients. It's really important. We do not take the coefficients into account. Coefficients are the numbers in front of a chemical. We ignore the coefficients when assigning oxidation numbers. Okay, let's figure out what got reduced, what got oxidized. We look for elements that changed. Some elements in some reactions will stay the same. This oxygen changed. It went from 0 to -2. Do you notice the number went down? It reduced. When the oxidation number goes down or reduces, that is reduction. Also, gaining electrons is reduction. Electrons are negative. If your charge gets more negative, that's reduction. Okay, the hydrogen went from 0 to +1. And we know that losing electrons is oxidation. If we lose an electron, we become more positive. Our oxidation number goes up. This did go up, so this is representing oxidation over here for the hydrogen. So now, hydrogen got oxidized. Notice I just wrote the element, not the entire compound. Hydrogen got oxidized. Let's look at, what's the definition? The thing that gets oxidized is the reducing agent. And it's the whole reactant. It's the whole reactant. So H2 is the reducing agent. If you get oxidized, you are the reducing agent. So let's check on the oxygen now. The oxygen, we look up here, got reduced. I just write the atom that got reduced. Oxygen got reduced. Now, the whole reactant, O2, and I don't need to include coefficients here. The whole reactant, let's see, if we got reduced, oops, sorry. If we got reduced, we're the oxidizing agent, and it's the whole reactant. We got reduced. There we go again. Sorry about that. So this is the oxidizing agent. And that's it. Oh, I'm not supposed to be recording that.